In this video, we're going to focus in on the structural features that lead to a strong base. So, in general, the strength of a base, which again is how much it can accept a hydrogen, depends on two things: the availability of lone pair electrons to form a bond. So, those electrons that are going to form the bond to the proton need to be readily available, and then the strength of the bond to the hydrogen. And so when we talk about this availability of the lone pair, what we're looking at is the electronegativity of the base. So the more electronegative it is, the tighter it's going to hold those electrons. They're going to be attracted very strongly to the nucleus of that atom, right? And so if they're more tightly held, if there's a stronger attraction, that means that they're going to be a little closer to the nucleus. And so they're not going to be available to form an attraction to another positive charge. Now, the less electronegative that base element is, then the easier it is for those electrons to actually participate in an attraction to another positive charge for the proton. We also see that if the lone pair on the base is delocalized, then it will actually reduce the availability of those electrons to form a bond, right? Because they're going to be kind of spread out. And so that delocalization that stabilizes a conjugate base and makes something more acidic. Well, the delocalization of an electron pair that's going to form a bond with the hydrogen decreases the basicity of it. It makes it less available to create that bond. Now, we also see that there's the strength of the bond to hydrogen. And so this is the bond that will form. So we evaluated before the strength of the bond between the hydrogen and the rest of the acid. And here we're saying, well, so what does the bond look like when it forms to the base, that hydrogen base bond? And here, again, like with the acid, we're going to be looking at bond strength in terms of bond length, really. Or bond, you can look at bond dissociation energy. I find for bases, it's easier to really look at the radius of the element, right? And so as that element is larger, it's going to have a longer bond length, which will be a weaker bond. And so as the radius of that base element gets smaller that has the lone pair, then the shorter the bond will be to a hydrogen atom and the stronger the bond will be. So let's compare. And first, we're going to compare water and ammonium. And then we'll do bromine and fluorine. And then we'll look at the lone pairs on methylamine and pyridine. So let's start with NH3 and H2O. So we're looking at really, so it's a lone pair on oxygen and a lone pair on nitrogen. And, and in this case, there is no delocalization, right? There's no resonance structures for either of these molecules. So we don't have to worry about that. We can look at the electronegativity. So our NH3 is going to have a lower electronegativity than our oxygen. And now we're trying to compare things that are similar. So these are both neutral atoms, right? If this oxygen atom had a negative charge, there would be a different set of structural features at play, right? The becoming a neutral molecule would be a driving force to form that bond to the hydrogen. But here we're looking at two neutral molecules, and so we can just compare the electronegativity. And the nitrogen here has a lower electronegativity, and so that means those electrons aren't held as tightly by the nitrogen. It makes them more available to form a bond to the hydrogen. And so it's going to make the NH3 a stronger base. All right, looking at bromine and fluorine. So here we have two ions, right? So they're both -1. Forming a bond to a hydrogen will make them neutral. So they have that same kind of driving force in terms of neutralizing their or having a zero charge. So the difference between these two really then comes down to their size. And here our fluorine is smaller. Therefore, the distance between the hydrogen and fluorine bond will be smaller. So that smaller bond length is actually going to create a stronger bond to the hydrogen atoms. The lone pair then is going to create, when it forms the bond, it'll be a stronger bond, so a stronger base. So in this case, the fluorine is going to be our stronger of the two possible bases. And this one's really comes down to size. All right, let's look at methylamine and pyridine. So looking at these two, I have a nitrogen that is, so this is really, I'll draw it out. It's a nitrogen that's in a conjugated ring system right here, bunch of hydrogens. And so in our pyridine, there is a resonance structure, right? We can shift all of these double bonds to where there's single bonds and then form single bonds. And so we have resonance structures that delocalize the lone pair on the nitrogen. Now, our methylamine doesn't have any multiple bonds. It doesn't have any resonance structures. And so the lone pair on the methylamine is localized on that nitrogen. And so it is more available to form a bond. It's not spread out over a six-membered ring. And so this lone pair here is more available. And so this will be the methylamine will be the stronger base.